Hi everyone. Am I audible? Yeah. So today I'll be talking about Go concurrency primitives, more specifically about when to use locks, how do you do lock-free programming, etc. So about me, so as I was already introduced, I am a code monkey at Last9 and hoping that by the time after a few years I start writing code as good as Shakespeare. So what's in for you today? So building a time series database at Last9, I started concurrent programming around 6 months back. Uh, with that experience, I learned a lot of to-dos and what not to do definitely while doing concurrent programming. So I'll be explaining and sharing those learnings with you and give you a go-to guide of what to do and what not to do. So for today's agenda, let's assume a problem statement of building a cache. Okay. Uh, and then we will go forward with what are the locking design patterns and lock-free design patterns for that. Some assumptions about the cache, how the cache should be. So since we want it to be thread safe. So if multiple threads want to read and write concurrently, that should be possible. Because cache generally is used at a scale, so definitely has to be thread safe. It is going to be a key value pair storage, and it must be scalable. By scalable, what I mean is a very precise definition would be that if I give more resources to the binary, it should proportionally scale and not be contended on any resource. So speaking more about the scenario, that would give us more context. So when to use a cache, first of all, our use case would be something similar to when we have frequent data retrieval. We need low latency. We cannot afford a network call or a database call for that. And our data is generally not changing. So it is a read heavy load mostly. So data is not changing and fewer writes comparatively. On the contrary, let's talk about when not to use cache. Demonetization, if you get the pun. Bad joke. Okay. What happens on cache invalidation? Any guesses? You go bald. Don't do it. Okay. So, jokes apart. Just setting a ground again, we are building a cache and we want to learn about locking design patterns first. So what is the first solution which comes to your mind when you say a cache? Like what is the most basic thing you would use? Anything? Maybe a hash map, which is directly available. But we had a requirement of it has to be thread safe. So using a Golang hash map directly will not be thread safe. So maybe we start with this. We use a mutex to protect that hash map. What happens here is you have multiple threads which are trying to read or write, but if a thread is already in transaction and has acquired the lock, everything else is blocked. Everyone waits for the lock. So, but this still has made my cache thread safe. And so at least I have one property of my cache solved, that it is thread safe. Now what I realized, we had already discussed that we have a infrequent changing data, that our read loads, it is read heavy then compared to the writes to the cache. So another idea is to use a RW mutex, correct? So let's do that. With a RW mutex, what will we achieve? So there are two locks now. Whenever a read lock is acquired, parallel reads can work at least. Earlier what was happening, if one thread is reading, no other thread can read or write either. Now at least we can parallelize the reads. But the other issue still exists, that if a write is going on, no other operation can happen on the lock. But at least our reads will become faster, which is our major load. So our RW mutex solves that, makes our reads parallel. So yeah, so at least another problem we have solved with this pattern, and right now it makes sense, right? How we are going about it. Then I have to decide, I want to go further. Now what do I do? So how locks work, right? Whenever there is a lock, even if you have say 64 cores on your machine, every thread stops at that one synchronization point of the lock because there's a single lock. So at that point, you are not doing any parallel work. So one of the things is when you are this duration for which you are holding the lock, so for this whole duration nothing is working in parallel, right? So how do we reduce the time for which the lock is acquired? One of the classic mistakes which I always did, I still keep it as a pattern in my book that I don't have to make this mistake. This is called optimistic locking. Okay, let's see what this is. So say for an example, your manager asks your team lead asks you to pay the AWS bill. Now all of them acknowledge and say, okay, we are on it. But an optimist on one side would say, ki, okay, I am hoping that somebody already did this. I'll just ask once. But I'm hoping that. This is an optimist speaking. Others are on it. So, yeah, for the example, right? So, the left diagram shows you that it checks that have I already paid the bill. I have a registry which maintains if I have already did this work for this tenant. If the answer is no, so this was the read happening, okay. First we read if the work is done. If no, we go and try to acquire a lock because it has to be done only once. I acquire the lock, I pay the bill or I create the resource. I write that I have created the resource and I unlock. This is my ideal flow which we were doing so far. Now what optimistic locking says that similar flow. You come again, you check that have you already done this? You say, no, it is not done yet. So the optimist first comes, sees it is not done yet. Then, so this is the first time when everybody gets a no for an answer. Then it acquires the lock. Now the optimist says that, okay, I'm hoping maybe somebody already did this. So he checks again that is this already done? And this makes sense, right? So if there was a thread who was holding a lock before you for the same purpose, you are sharing a lock because you are doing the same work. So it is possible that the thread before you who was holding the lock has already done the work for you. So this is a classic mistake which everyone misses, that you don't realize, you don't recheck it again. So what we end up doing in some cases is pay the bill again. So somebody had already did that and you again pay the bill. So yeah, so here you have an early exit. When you ask that question that is it already done? So you get an early exit and you unlock early. Versus if the answer is still no, you go by the same cycle. But here you have that benefit that you get an early exit plus you are not doing a wrongful transaction. Correct? So yeah. So optimistic locking solved this, avoids duplicate resource creation. In our example, we did not pay the bill 2 times because of that. And it reduces the duration for which the lock is held. You acquire the lock, but then you leave early. Because at lot of places, this cycle of creation of resource can also be time consuming. So this way, we also reduce the amount of time for which the amount of time duration spent in the critical section. Okay. Now, okay, spoiler. So right now, we say that everyone in the whole room, everyone say you guys want to have food. We have only one queue, but there are 4 counters later. Like we have the ability to do that, okay. That there's veg and non-veg food is different, but you are still in a single queue. Now in some cases you have a logical separation that you can actually separate out the load, right? So take for an example, say you have multiple organizations on your software or multiple tenants running. So when you're doing work of one tenant, so basically when I say multiple tenants, the data of course is isolated, either logically or physically itself. So in this case, since the data is separate, you can actually ideally just separate out the logs for both of these, correct? So this is also one of the classic things which we miss on, that because if you're doing work for say A tenant is continuously hitting requests, and B tenant sends request once in a while. So it is possible that B tenant never gets a chance to execute because the A tenant continuously holds the lock, releases it. So we can actually separate out this, and because the data is not shared, so we can do this very easily. So what we say, we make granular locks. Everybody gets a lock. Okay. Then, so yeah, this is how this works. So say on the right hand side, you see that the data shards are different. Correct? Assume that that could be logically separated, tenant 1, tenant 2, tenant 3, etc. So we separate out the locks as well. And there should be a lock registry to hold these locks as well, right? Acquiring, so in this case, even choosing what lock to acquire, that also needs synchronization. So the first thing written over here, lock registry, that itself has to be thread safe. First, what any request come, it sees that okay, I am tenant 1. I'll first get the what lock I should use. Then I will start to acquire it if I need to. I'll read. We can combine all the approaches which we discussed before. We can use a RW mutex with optimistic locking and with sharded locks. So I fetch what lock I need to use, I start acquiring, I read, I start acquiring it. So all of this is separate now. At least we have some kind of, we have reduced the contention. Earlier, there were 8 lanes on a highway, all stopped at 1 fast lane. Now at least we have 3-4 fast-tag lanes. So at least that has improved. We have distributed the lock contention in our system. So is this clear? All good? So yeah, we saw all the locking design patterns, but there are still some problems. We optimized a lot, but there are still few problems which we observed in our system. One of them is there is unsteady CPU usage. So why is this? Assume, like imagine that same thing, right? Multiple threads, all sleeping, staying idle at the same time. CPU is not getting used altogether. And once the gate opens, everything flushes out together. So there is unsteady usage, plus there is a spike. So in this case, even if your software requires say 2 vCPUs of load, like requires only 2 cores of CPU, but because you have these spikes that suddenly, first of all, nothing is getting used, and suddenly you use 4 vCPUs worth of CPU, so things start getting slower. So ideally you would want that you, you allocate as per those spikes as well, that even though whenever I open, I want to make sure that I don't run slow because lack of CPU time. Then again the same thing, because of synchronization, at that synchronous point we don't make use of all the processors or cores available to us, and there's no independent progress on the thread, that if thread A is doing this, like thread B ka progress is dependent on another thread as well if someone else is holding the lock. So these are the problems we have observed with locks. So we want to go a step further. Why go to lock free? Right? Because we have these problems, we still have some problems with locks. So let's look at lock-free design patterns. So these lock-free design patterns are not some kind of magic, right? We either do synchronization at the software level or we do at the hardware level. At lot of hardware chips give you synchronization primitives like atomic operations and CAS. So as far as I know, CAS is only available on ARM. So it is a single instruction. So when you say, so you know instructions have add, subtract, etc. So this CAS is a single instruction. It will read, compare and then swap if needed. And same as atomic operations. So the special thing about how are these different, right? Since we are not using locks, these are not waiting. You have wait free. You don't have to really wait to acquire the lock. So there's no much CPU contention over here. Although because it is synchronization, it is possible that 2 threads are calling compare and swap, and one of them succeeds. So the other one will fail because the value is changed. So in compare and swap, what you do is you give the old value and the new value. So if the old value does not match what is in the memory, then it fails. But at least here you don't have to stay blocked. It is not, it is wait free. So you can retry in this case. As per your convenience, you can add, you can manage that, right? You can add exponential back off in your retries, etc. That is in your hand. You at least have some option to do something about it. And as I mentioned, in case of conflict between two atomic operations as well, both of them will roll back. So yeah, this is one of the example. So in the first case, right, in the first part of it, two operations are made. One of them is doing compare and swap, another is doing an atomic operation. Both of them try to modify the same resource. So both of them fail at the end. Both of them roll back. Then independently, when they try to make the change, they are successful. So how do we actually use it, right? So this is one of the classic patterns, atomic snapshots. So assume you have a cache, right? You have two hash maps. Both are, you can actually get rid of lock altogether over here. So when do we get data races? When you are concurrently reading and writing, correct? What if we separate out the copies of read and write? That we say we start, we first have an empty read hash map, and in one of them we are just keeping on writing. After a while we refresh, we run a background process, a goroutine per se, which reads the right copy, like keeps on refreshing, creates a copy of the right copy, and then does an atomic swap of the read copy. So your read copy keeps on getting updated every refresh interval as per your configuration. This is one of the patterns. So if you see on the left, I have shown you what is happening on the read side, that you have a read copy, all the threads are without any lock, they are reading from the read copy. On the right, all the writes are being returned to a buffer, and then so there is a single writer. This is a classic pattern, which is why I have mentioned that buffer as well. You keep on writing to the cache, and in between there is a process which keeps on creating a copy and swaps your read copy. So this is completely lock free. There are some places where you might get stale data because your read copy is running behind by some milliseconds. But this is very useful when, again, we have a read heavy load. So this is not really going to make that much of a difference. And you can trade off on that, how frequently you want to update the copy, etc. So what are the problems with this, you think? Definitely, if we have to compromise on something. So since we constantly keep on creating a copy of the right copy, the CPU and memory usage increases. The memory is definitely double of what we have, correct? The write copy say holds 10 items, we create a copy of it for the read on, and so there is double CPU usage there. And sometimes if you do this very frequently, right, your CPU also gets used a lot because of all the operations of copying, etc. So, but this is one of the classic patterns which we have used and was helpful. Yeah, so anything on this? This is a very good use of the compare and swap. You create a copy, compare and swap, etc. Another pattern is using atomics with arrays. So what is different between a hash map and array? So with an array, what happens is every element in the array is a separate memory item. So you can actually access concurrently all the items of the array. So here is an example, right? When your thread is not concurrently accessing the same element of the array, then you are good over here. Versus, so the first section, right, that just only one thread is accessing one index at a time. In the second one, we are accessing two items of the array within the same goroutine. So they are concurrently being accessed. So that fails. So what we can do is, what if we, atomics are very lightweight. In Go, if you know, the sync package gives you all the data types, right? uint 64, uint 32. So you can make an array of, say, uint 32, and you do a atomic operation on every array element. So you don't have to use lock. And plus, your say you have hundreds of operations happening on your array. There's no single lock synchronizing them. Every element index has its own synchronization on memory level, right, with the atomic primitive. So this is also one of the classic patterns we have used in production to solve our problems. So these are some of the array-based data structures which are built, and most of the implementations what you find are log-based, but this can be very easily done with atomics and cas. These are some of the data structures. We'll look at one of the data structure, a case study for that. So this is a case study of how Bloom filters are used. I just wanted to add this to show that this is actually something you can use in production, and Bloom filters are really used at a scale for like for your operations, whatever. So say this is the setup, right? You have a database and you want to read data from it. You also always have generally have a cache when you are serving on a very high scale. So how do we decide that if we need to go to the database? So Bloom filter is a data structure which can give you two answers, one probabilistically, one definitely. So it can tell you that I've definitely not seen this query before. What it does is, so let me give you an example. So say you have an array of 10 elements. You add apple to it. So what it does is you have two hash functions, okay? Apple hash returns 2, number 2 as the hash, and the hash function 2 on apple returns 3. So what you do in the array, you go and set 2 and 3 as, set the bits as 1 on the Bloom filter. Now when you have to check that have I seen apple before, what can you do? You can simply create the hash again and check if the bits are set to 1. So this can definitely tell you when something is, so if I see that the bits are not set, then I'm very sure that I have not seen this before, right? So Bloom filters, this gives you a context of what Bloom filters are. Now we can use this to know that have I seen this query before. If I've definitely not seen this before, I then have to definitely go to the database. Correct? So when I ask that is it present in cache, it says no, it is, when it says no, it is sure it is right. But when it says yet, it is probabilistic. Because your hash bits might collide, right? Apple ka hash function 2 can yield 3, and orange ka apple, like hash, basically hashes can collide. The operations we do to set the bits, we take a mod, etc. I don't want to deep dive into Bloom filters, but it is fairly straightforward. I can add the references. Correct. So this is one of the classic usages of Bloom filters, and since we saw that how can we create Bloom filters which are log free, this gives a very good use case you can use in production. Yeah. So this is these are the things which I have learned and which I have seen very commonly in my work, that I come across these again and again. So the learnings are that Go gives you very good concurrency primitives, easy to use, because I genuinely have just started 6 months back doing all this concurrent programming, and it was very easy to just get started with it. There is always a scope of improvement. Like I think I've reached here, and I'm pretty sure that like lot of things which I've yet not explored, but Go has all the support. So you can keep on improving always, and it is very addictive. When you start looking at those pprof charts, you see, okay, this is going wrong. You run the benchmarks again and again, but you need to know when to stop, only until it adds value to your customer or reduces your costs. And you need to know your problem domain. So here you saw that a lot of decisions were made because we knew that our read load is heavy versus write load, correct? So these kind of things give you a very good idea about the bottlenecks as well, right? We understood that, okay, since there is a logical separation between data, we don't really need to have a common log. So understanding these traffic patterns with your data, that also helps you a lot in making these decisions, what pattern to use. So one of the references which I was forced to read, which is very nice book, is this, The Art of Multiprocessor Programming. It is very written in very simple words. You should definitely check it out. Yeah. And yeah, that's it. Thank you.